we start this section by talking about limit laws. And these laws will help us evaluate complicated limits that would involve different math operations. So we'll start with the limit of a constant. So let's say you have f of x equals c, and c could be some number like 5. So the way you'd find the limit of a constant is, let's say the limit as x approaches a for f of x would be equal to the limit as x approaches a for the constant. And if you think about this, this would just be graphically just a horizontal line at c. And so if you're approaching a from both sides, you end up just approaching c. Okay, next, the identity function, y equals x. If we were to find the limit as x approaches a for this function, this would be the limit as x approaches a for x, and this would just involve us plugging in, doing direct substitution into the function, and so it would just be a as the limit. All right, so let's say we're trying to find the limit of a sum or difference of two different functions. What's nice is we can actually find the limit separately for f of x and then add or subtract that limit to the limit as x approaches the same value for g of x. Okay. Similar law can be applied to the product of two functions when you're trying to find the limit. So if you're finding the limit as x approaches a for f of x g of x, this is nice that we can just find the limit as x approaches a for f of x and multiply that to the limit as x approaches a for g of x. All right, if we have a monomial, the limit as x approaches a for some coefficient c times x to the n, we can just plug in the value we're approaching. So this is c times a to the n power. And if we have a polynomial, which a monomial is a type of polynomial, we essentially just need to plug in the value that we're approaching into the polynomial, and that'll tell us the limit. If we have a function raised to a power and we're trying to find the limit, what's nice is we can actually find the limit of the function and then raise that to a power. And so that comes in handy in various situations. And same thing can be applied to a root of a function. We can find the limit first of a function and then take the nth root of that limit. And then lastly, our last limit law is the quotient rule. So if we're taking the limit of a fraction of two different functions, we can actually find the limit separately of the numerator and the limit of the denominator. And then divide the two, as long as the limit of g of x does not equal 0. That's sufficient. Okay, so a couple examples down below. So we have the limit as x approaches 2 for 7, which is a constant. So we discussed that being the first rule. It would just be 7. The limit as x approaches 2 for x would be 2. You plug 2 in for x. Okay. The limit as x approaches 2 for the function x minus 5. So we can apply the sum slash difference rule, the law number 3 above. And so we can separate it to be the limit as x approaches 2 for x minus the limit as x approaches 2 for 5. And so this would just be 2 minus 5, which is negative 3. Okay, and then on D we have a polynomial or a monomial. And so what we can do is we can just plug in the 3 that we're approaching. So it'd be negative 5 times 3, which is negative 15. One thing to note is that anytime you have a constant like this or a coefficient, you can take that outside the limit. So just to show this as a useful skill, we can say negative 5 times the limit as x approaches 3 for x. And so this would be negative 5 times plug in a 3 into the function, and you can see we get the same thing. And lastly, we're going to apply the quotient rule here. And so we can find the limit as x approaches 2 for x in the numerator, and then find the limit as x approaches 2 for x plus 3 in the denominator. And so we just plug in the value we're approaching in the numerator, same thing in the denominator, and we get 2/5 as the limit. Here we're going to talk about different algebraic techniques that can allow us to find limits. So the first technique is always to try to directly plug in the value that we're approaching. And so as long as the function is continuous at that point, we should have no problem plugging it in and finding the limit. So here we know we have a polynomial function, and we know polynomial functions are continuous for their entire domain. So there's no problem just plugging in the value that we're approaching. And so the limit for this is just 34. For part B, it's a rational function, and rational functions are known to have discontinuities. But same as part A, as long as we can plug in the value we're approaching, get a number that's not undefined, that will be the limit. So we'll plug in the value, and as long as we don't get undefined, we are okay. And so we get 12 over 39, which simplifies to 4 over 13. If we look at the piecewise function, we're trying to find the two one-sided limits and then the two-sided limit. So if we're trying to find the limit as x approaches 1 from the right side, those would be numbers greater than 1, so we want to plug into the bottom piece. And so that would be the square root of 1 minus 1, which is 0. So that's the limit as x approaches 1 from the right of f of x. As we look at the next limit, the limit as x approaches 1 from the left, we would want to look at the top piece because its restricted domain is for numbers that are less than 1, right? And so if we're trying to find the limit as x approaches 1 from the left, this is the equation we'd want to plug into. So we're going to plug in 1 into the top piece, and so the limit as x approaches 1 from the left is 2. And so since the one-sided limits as x approaches 1 do not equal each other, we know the two-sided limit does not exist. All right, so if plugging in does not work, we have to rely on other algebraic techniques. And so the first technique that we discuss is factoring out, or factoring and then trying to divide out any factors. So here, if we plug in 3 into the function, we always try to do the first method. So if we plug in 3, we get 0 over 0, which is called the indeterminate form. And that doesn't mean the limit does not exist. It typically means there's some algebra we can do to find the limit. So we're going to factor. So don't forget to write the limit. That doesn't go away until we can do direct substitution. So we're going to factor the numerator. It's the difference of squares. And here we can see the x minus 3 factor cancels out. And so since we're left with the limit as x approaches 3 for x plus 3, this is okay to plug into. So now we can directly plug in to the expression that's left and see that the limit is 6. All right. So even though the function's undefined, right, like this, that's here, right, when we plug in 3, we get 0, 0, which is undefined. That doesn't mean the limit doesn't exist. So typically when we plug into a rational function and get 0, 0, that typically means there's a hole happening. So something like this graph off to the side is a good representation of what's happening. So f of a is undefined in this photograph, or this picture, but the limit does exist, and it is approaching some value. So let's look at part B. So part B, if you plug in the x value you're approaching, 2, you will get 0, 0, which means there's probably some algebra we can do. So we're going to factor by grouping. So we can take an x squared out of the first two terms of the numerator. We can take a 4 out of the next two terms. In the denominator, same thing, we're going to factor by grouping, so we're going to take an x cubed out of the first two terms. And the next set of terms, nothing to take out. I'm just going to factor a 1 out, just to make the factoring easy on the next line. All right, don't forget the limit. The limit as x approaches 2 for x squared plus 4 times x minus 2 over x cubed plus 1 times x minus 2. All right, so we see the x minus 2 factor cancels out, and that was the issue, right, of us plugging 2 in. So now, since that goes away, we can plug in the value into the expression that's left. And so we get 2 squared plus 4 over 2 cubed plus 1, which turns into 8 over 9. Okay. And then one more example regarding factoring. And so this is a one-sided limit. The limit as x approaches 2 from the right side for this function. And we always try the same techniques. We always try to do direct substitution. So we would plug in 2, because if the normal two-sided limit exists, then the one-sided limit should exist and equal the same number. So we try directly plugging 2 in. We get 0 or 0. And then we move on to factoring if we can. So we can factor both the numerator and denominator. We can take a 4 out of the denominator. Let's see. And we'll factor that trinomial in the denominator further. So 4 times x plus 7, x minus 2. And notice once again this factor goes away. That was the issue of us plugging 2 in the beginning. So now we should be okay to plug in. So we'll plug in the 2 into what's left. So we get 2 plus 3 over 4 times 2 plus 7. So that gets us a limit of 5 over 36. Other techniques that we use are rationalizing techniques. If we see a radical involved in the function that we're trying to take the limit of. And one of the techniques that we use is we multiply the conjugate of whatever line, the numerator, denominator, whichever has the radical involved. That's what we multiply the conjugate by. And so what's the conjugate? You hopefully recall this from Algebra 2 or pre-cal. A conjugate would be something like if you have a binomial of x plus 5, the conjugate to x plus 5 would be the same thing. You just change the sign that was separating the two terms. So the conjugate to x plus 5 is x minus 5. And remember, the nice thing about multiplying conjugates is the middle term will zero out. So if you were to multiply those together, you would just end up with x squared minus 25. And so that's important to remember as we go forward. So on part A, if we're trying to take the limits that x approaches 4 for that function, you still try to do direct substitution if you can. And so if you plug in 4, you will get 0 is 0. And so the algebra we want to apply is we want to multiply, don't forget the limit notation, we want to multiply the fraction by the conjugate of the numerator, because that has the radical. So the conjugate of root x minus 2 would be root x plus 2. And so if we multiply the top by that, we have to multiply the bottom as well to not change anything about the function. We're just trying to modify its form. And so we're going to multiply only the line that has the conjugate. So we're going to multiply only the top here. So remember, the middle term will go away. It'll zero out. So we have the limit as x approaches 4 for root x times root x is just x, and then minus 2 times 2 is minus 4. And the denominator we're going to leave in factored form, because you can hopefully see that when we do that, this factor cancels out, which was the issue of us plugging in 4 in the first place. And so now that that's gone away, we can just plug in. So remember, when those factors cancel it out, there's still a 1 in the numerator. Over, plug in the 4 we're approaching, and that gets us 1/4. Alright, so on the next example, we still try to plug in the value we're approaching, 16, through direct substitution. We'll get 0 is 0, so that's not a surprise. But now it allows us to go further with algebra. So we're going to multiply, this time, the denominator by the conjugate. So I'm just rewriting the function. And we're going to multiply the fraction by 4 plus root x on top and bottom. All right, so we are only going to multiply the line with the conjugates. And so, don't forget the limit notation. So we'll get 16 minus x, and the numerator, we'll leave it in factored form. Okay? All right, what goes away? All right, the 16 minus x factor. And again, that was the issue of us plugging in the value we're approaching. And now we can plug in the 16 into the expression that's left and get an answer of 8. All right, other algebra techniques. So sometimes we have to do other types of algebra. First technique, still the same. We try to directly plug in the value we're approaching. So if we plug in 2, we'll get 0 is 0. And anytime we have fractions within a fraction, within a larger fraction, we try to combine the smaller fractions through getting a common denominator. So we're going to multiply this first fraction by 4 over 4, and the second fraction by x plus 2 over x plus 2. Okay, so this is going to equal the limit as x approaches 2 for 4 minus x plus 2 over 4 times x plus 2. So those two smaller fractions have combined now to 1 all over x minus 2, but we can make it be times 1 over x minus 2. Okay, let's see what cleans up here. We're going to simplify this line right here. So don't forget the limit notation. Limit as x approaches 2 for negative x plus 2 over 4 times x plus 2. Okay, so in order to get the x plus 2 factor to divide out, we're going to need to factor out a negative out of the numerator. Okay. Oh, I forgot on the previous line to carry the 1 over x minus 2. Okay, 4 times. All right, so now we can see the x minus 2 factor will divide out. All right, and then that allows us to plug in. So we'll have negative 1 over 4 times 2 plus 2. So 2 plus 2 is 4. 4 times 4 is 16. So the limit is negative 1 over 16. For this next problem, we're going to review Pascal's triangle. And so Pascal's triangle will tell you the coefficients of expanding a binomial. So Pascal's triangle starts off 1, 1, 1, 1, 1 on the second row. And then you add together 1, 1 to get 2, the middle number, still surrounded by these 1s. And so that's the third row. And then the fourth row, same thing, you have 1s on the ends. You add the 1 and the 2 together to get that 3. You add the 2 and the 1 together to get that 3, and so forth. And so the next row of Pascal's triangle would be 1, 4, 6, 4, 1. And these are telling you the coefficients of a binomial to the nth power. So if you're having a plus b to the third power, this would be the row you would look at for the coefficients, because the first row is to the 0th power, and then the first, second, third. So let's do an example of using Pascal's triangle to expand a binomial. So let's say we have 2 plus h cubed. And so we are looking at that fourth row that I've circled because it's to the third power. And so we start with that coefficient, that 1, and then we take the first term of the binomial, 2, raise it to the power that the binomial is being raised to, and then the last term of the binomial, h, is raised to the 0th power. And so it follows this pattern. So the next term would be 3 as the next term in the row of Pascal's triangle that we're focused on, times 2, the first term of the binomial, to the second power. So it goes in descending order. So it'll be 3, 2, 1, 0 as we get these terms of the expansion. And then it'd be h to the first. So this is going to increase from 0, 1, 2, 3. Okay, so let's continue. Okay. So it'd be plus 3 times 2 to the first times h squared plus 1 times 2 to the 0 times h cubed. All right, I'm going to clean it up. And so this would be 8 plus 12h plus 6h squared plus h cubed. All right. So let's look at this problem finally. Okay. So that was just a review of Pascal's triangle to expand binomials. Okay, so now we're looking at, okay, given f of x equals x cubed minus 1, I want to find the limit as h approaches 0 for f of 2 plus h minus f of 2. Okay, so we're going to take this slowly. Let's find f of 2 plus h first. So this would be 2 plus h cubed minus 1. So the example that we did has 2 plus h cubed already expanded using Pascal's triangle. So we got 8 plus 12h plus 6h squared plus h cubed minus 1. All right, and then f of 2, let's see, that would be 2 cubed minus 1, which is 8 minus 1, which is 7. All right, okay, so now let's evaluate this limit. Okay, so the limit as h approaches 0 for, okay, let's plug in what we know f of 2 plus h is, which is this expression. So 8 plus 12h plus 6h squared plus h cubed minus 1. Okay, minus the 7 all over h. Okay, so we can't plug h in right away because we would get 0 over 0. So there must be some algebra we can do here. Okay, so let's combine what we can in the numerator. So we'll notice that 8 minus 1 is 7. Minus 7 will just 0 out. And then we're left with these 3 terms. And they all have an h involved. So we can factor out the h in the numerator. And then we notice the h's right here will go away. They'll divide out. And that'll allow us to plug in h approaching 0. We'll be able to plug in 0 for h. So we'll end up equaling 12 because these 2 terms will just 0 out. This time we're going to be given the limits of 2 different functions as x approaches 0 for both of them. And we're going to use those to our advantage with the limit laws to help us evaluate. So, okay, looking at the first one, the limit as x approaches 0 for sine squared x over x. So notice it looks very similar to this function for this limit. And so what we can do is we can use the product law of limits. So we'll separate it into sine x over x. So we'll take the limit as x approaches 0 for that, times the limit as x approaches 0 for sine x. Okay, and so we know the first limit is 1 because that was given to us. And then the second limit, we can just plug in the sine of 0 is 0. And so 1 times 0 is 0. All right, moving on. The next one, we have the limit as x approaches 0 for 1 minus cosine x over x. So it looks very similar to this given limit. And there's a couple ways we could solve this. I think the easiest way we could solve it is we could recognize to factor out a negative out of the numerator such that it matches that numerator of the given limit. Right? And so, again, just using the product law of limits, or we could just take a -1 out, like I mentioned earlier. That might be easier. Let's do that. Okay, we'll just take the -1 outside the limit times the limit as x approaches 0 for cosine x minus 1 over x. All right, so we know the limit, because it was given to us, was 0. So it just equals 0. All right, moving on. On number 3, what we should recognize is sine of 2x is a double angle identity. So right off the bat, we're gonna change the numerator to be 2 sine x cosine x, right, based off the double angle identity. And then, once again, we're going to try to use the product limit law. All right, so I recognize sine x over x is that first given limit. So that's what my thought process is here. So we'll find the limit as x approaches 0 for sine x over x. And what's left is the limit as x approaches 0 for 2 cosine x. All right. So the first limit we know is given to be 1. And then the limit as x approaches 0 for 2 cosine x, we can just plug in 0. And so 2 times cosine of 0 is 2, right? Because cosine of 0 is 1, so 2 times 1 is 2. So 1 times 2 is what we have. So this equals 2. Finally, something other than 0. All right, moving on. Number 4. So this one's a little bit more complicated than number 2, which has that same numerator. And so the strategy here is we're going to multiply the fraction by 1 plus cosine x on top and bottom, because this will get us the difference of squares in the numerator, which is an identity that we can utilize. So, all right, let's do this. So the limit as x approaches 0 for 1 minus cosine squared x over x squared times 1 plus cosine x. All right. So we know the numerator, 1 minus cosine squared x, can be simplified to just sine squared x, right? Based off the sine squared plus cosine squared equals 1 identity, the Pythagorean identity. So that's what we're going to do next. So I'm just rewriting the denominator. All right, and we're going to now try to utilize the first given limit. So I can see we can separate it, what we currently have, to 2 of these sine x over x's. So let me write that out if that's confusing. Okay, so continuing on. Again, don't forget the limit notation. Equals the limit as x approaches 0 for sine x over x times the limit as x approaches 0 for sine x over x. So I essentially just separated what I highlighted into 2 different limits. And okay, what do we have left? So we're just using the product law here of limits. So the limit is x approaches 0 for 1 over 1 plus cosine x. Okay. So what do we have? Okay, so the given limit, being these first 2, right, it's just 1. So we got 1 times 1. And then the limit is x approaches 0 for 1 over 1 plus cosine x. We can just plug in 0 here. And so cosine of 0 is 1. So 1 plus 1 is 2 in the bottom. So we get a half on that last limit. So that multiplies to get us 1/2. Okay, last question for this page. We've got the limit is x approaches 0 for x cosine x minus sine x over x cosine x. What I see here is we can separate this into two fractions, because when I do that, what I have circled, that fraction, you can see cancels out to become 1. That makes our life a lot easier. So that's what we're going to do here. So we're going to separate it into two fractions. Okay, so what do we have here? We got the limit as x approaches 0 for x cosine x over x cosine x minus the limit as x approaches 0 for sine x x cosine x. Okay, so this first limit simplifies to just be 1, right? Because they just completely cancel out. And then on the second limit, we're gonna separate it, because we notice sine x over x here is that given limit that we're working with. So let's do that. The limit as x approaches 0 for sine x over x. And what's left? Still just using the product rule, the product law. We got 1 over cosine x left. Okay, so what do we know? Okay, so the limit as x approaches 0 for our constant 1 would just be 1 minus sine x over the limit as x approaches 0 for sine x over x. We know that was 1. That was the first given limit. And then if we plug in 0 here, cosine of 0 is 1. So 1 over 1 is 1. All right, so 1 minus 1 is 0. All right, so on this side, we're going to look at composite limits. And so we'll look at first a problem that you've seen in Algebra 2 or pre-calculus. And so you'll remember to solve this composite, you want to evaluate the inner part first. So we want to find g of 4 first. And keep in mind, 4 is an x value. We're looking for the corresponding y value on the g graph. And so we can see that it's -1. So now, that y value, right? So we're looking now for f of -1. So keep in mind that was a y value on the g graph, but now it's acting as an input value, so it's going to be an x value for the f graph. So we're looking now for f of -1, and we can see it's that corresponding y value I have circled, which is 3. Okay, so limits, composite limits operate very similar. So one thing to note is when you're taking the limit, for instance, as x approaches -3, we want to first find the limit as x approaches -3 for g of x. So let's do that. So I'm just going to work this separately. So the limit as x approaches -3 of g of x. And so we can see from the left side, as we approach -3, from the left, we're approaching a y value of -2, and then same from the right. And so we have to be careful, because remember, this y value that we're approaching on the g graph is going to correspond to an x value on the f graph, the f function. So we need to pay attention to where is g approaching this y value of -2 from. So if you look, we're approaching this y value of -2 from above. So this is going to correspond to an x value on f of x. So now we're looking for the limit as x approaches -2 from above. Or not from above, but from the right side now, since we're worried about the x value on the f of x. So if we look now at the f graph, at -2. Following it in from the right side, we can see we're approaching a y value of 3. Okay. Let's look at number 3. So we'll take the same approach on number 3. We want to find the limit as x approaches -1 first for g of x. Okay, so the limit as x approaches -1 for g of x. All right, so there's -1, and we can see we're approaching from the left and the right a y value of 4. And so again, we have to be careful. Are we approaching that y value from below or above? And so you can see we're approaching 4 from below. And so I'm going to put this superscript of a minus there so I don't forget it when I take the limit as x approaches 4 from the left now of f of x. So 4 is here, and so from the left we're approaching a y value of 2 on the f graph. Okay, all right, last one, number 4. We want to find, okay, the limit as x approaches 0 for f of x squared plus 4. So first we're going to find the limit as x approaches 0 for the inner function. And so we're going to focus on that first. So the limit as x approaches 0 for x squared plus 4. And you might be thinking, well, I can just plug 0 in because of direct substitution, because of polynomial, which is true. And we know it would be 4. But we have to be aware of if it's approaching 4 from above or below. So we're going to draw a quick sketch of this graph. So we know it's a parabola that opens up, has a y-intercept of 4. And so you can see as we approach 0, we are approaching 4 from above. So when I take the limit as x approaches 4, it needs to be from the right side on the f graph. So from the right side, we're approaching a y value of 1.